Hello, I am Ethan. Joining me will be my colleagues, Ivan and Isaac. Together, we are excited to delve into the technical presentation for the development of Neonode's frontend. To start things off, we will provide an extensive overview of the technologies that have powered the creation of Neonode. Neonode's frontend is created using React Native as it is widely used and extremely reliable, being compatible with both iOS and Android, which encompasses most of today's phones' operating software. ExpoGo provides us with a speedy development build time as ExpoGo allows us to execute JavaScript without having to wait for the build process, which in turn speeds up the testing process of Neonode. On top of that, it also provides developers with a QR code that can be used to test user interfaces directly. ExpoGo also has extensive choice of libraries that we can use. We implemented audio, image picker, and haptics. More on that later. We have decided to use Tailwind CSS for the styling aspect of Neonode, as it is an incredibly lightweight and easy to implement technology that allows us to predetermine color codes and styles that can be directly used on any component by utilizing the name of the style within the class name of the object to ensure consistent styling. Moving on to the app.js, we orchestrate the navigation structure of our application, opting for the utilization of a stack navigator. The Stack Navigator framework provides a way for our application to transition between screens where each new screen is systematically layered atop an existing stack. The reason we use a Stack Navigator is that it aligns well with the structural requirements for our application. It allows you to easily push and pop screens onto and off to the navigation stack, reflecting a behavior that is expected and familiar to users. Furthermore, Stack Navigators typically manage memory efficiently by unloading screens from memory when they are popped off the stack, thus ensuring optimal resource utilization and performance. Here is the login. As you can see, we are using the Firebase authentication. Firebase authentication is very popular, and there are many reasons why we chose this. First and foremost, Firebase authentication excels in cross-platform compatibility, seamlessly extending its support to both iOS and Android environments. Furthermore, the selection of Firebase authentication hinges on its robust security architecture, which adeptly mitigates authentication vulnerabilities, including, but not limited to, brute force attacks and account enumeration. Also, as you can see, we are also using Stack Navigation that will point you to either creating your account in signup or the home page if your login is successful. In the homepage, we employ a variety of React Native components, including view, text input, touchable opacity, scroll view, status bar, to build the interface that was imagined in the final prototype. The React Native framework creates an accessible and efficient way to construct these interfaces. Moving on to the notes itself, we maintain an array of notes objects in the note state variable. Each note has an index, a note, including the note's content, and is favorite, a Boolean value to indicate whether note is favorited. The array-based storage significantly streamlines note deletion operations. When a note is deleted, the array of notes will reorder, with the deleted note replaced by the subsequent one in the array. We can delete notes by using onLong press with the touch opacity element. This will be handled by a delete note handler function, which will delete the note corresponding to the index and the note content. Furthermore, we have implemented a search feature that employs a text input element. The search results are then stored in the filtered note state variable, ensuring that the displayed notes correspond to the character sequence entered in the search bar. To enhance user interaction, we have integrated a toggle favorite function that allows the user to modify the favorite status of the note. Lastly, we implemented haptic feedback on the toggle favorite function. When a user marks a note as a favorite within the home menu, there's a tactile response that is felt.
Hello, my name is Ivan and I'll be talking more about the note and block structure within Neonode. Within each note, we have decided to break it down into multiple blocks, allowing users to create, delete, and also move blocks around as they wish. These blocks allows developers to differentiate between each block and the content type within each block, such as text, image, or voice memos. With the creation of a new block, it is appended into the array and stored. Creating a text block is very straightforward, a block object that stores a string. With Voice Memo, it uses Expo AV Audio Library to record and store the audio object into the content of the block. Expo Go's audio library was the most appropriate library to be used as we run NeoNote off of Expo Go, making it compatible and incredibly effective and fast to implement, and also helps prevent any compatibility issues with audio recording. Together with that, once the audio has been recorded and stored, there is no need for another external library to be used to replay this, as Expo AV provides functionalities to replay the audio effectively. Once the audio is recorded asynchronously, the recording object is disposed to ensure that there is nothing passively active in the background to ensure performance is maintained. The audio object is then stored in the block to be replayed by the user. With the implementation of the voice memo, it made the implementation of voice to text a lot easier, as we use the same function to record the audio file, which is then sent to the Python script through Fast API for the Google voice to text function to return the detected words. This implementation is extremely straightforward and easy to understand, fast in performance, and efficient in development. Moving on to the system development process of NeoNote, we've decided to build each functionality and have it work as intended before moving on to another functionality. This ensures that all of our functions are built and working as intended before we move on to another component. Together with that, it also provides us with knowledge of any issues or problems that we encounter being directly related to the functionality that we are currently implementing, preventing any confusion and waste of resources. We started our development process of the front end by designing the note adding and creation functionalities. Once we're able to type into these blocks, the next step is saving these notes to the backend properly, which will be discussed further in the backend technical exploration. With the completion of these functionalities, we are now able to move onto other functionalities without needing to worry about the communication between the front end and the backend. Next step is to implement multimedia into NeoNote without sacrificing performance and speed. With multimedia storage, the content of the blocks stores voice objects and image objects containing data and information of the files respectively. With the backend endpoints all fully functioning to receive and store data, saving these multimedia into the database was a lot easier to implement. Our main takeaway from the development process of NeoNote is to establish a foundation to produce each functionality step by step to ensure errors and bugs are identified and can be quickly traced back to the source, allowing us to quickly rectify the problems and mitigate the amount of time spent on fixing bugs, making development processes much more efficient.
Hi, I'm Isaac. I'm going to be going through the Python script. The Python scripts were used to handle the AI functions such as voice to text and image to text through Fast API, which is a RESTful API where we have access to use Google Tesseract for our AI to return a text-based output from images, and Cloud Speech to return text-based outputs on voice recordings. The API is used to send a request from our React Native frontend to the Python script, which is done with Axios, which allows us to post to our VPS where our Python script is running and get the text returned to our frontend where the text returned is set into the block. We have decided to create our own script to handle the AI functionality, as the external libraries from React and Expo have not been the most reliable and oftentimes causes incompatibility issues between React Native and Expo Go, especially when it comes to accessing permissions for devices. Therefore, we have opted to stick with Python scripts which handle and return the data as a response to be handled in the front end. This has proven to be incredibly effective and maintains the swift responsiveness in the front end, which is NeoNote's goal. We use photonote.jsx to allow the user to access their camera while in NeoNote and have a full screen view of the camera by having its own JSX. We use Expo Camera for its ease of use and compatibility with Expo Go. First, we get permissions from the user. When we get the permissions, we allow the user to take a photo with the photo button on the right and back button on the bottom right. This is done due to limitations where you can style the buttons with Expo Camera. The photo button is kept in the middle so the user can take a photo easily, and the back button is at the bottom so users have to go out of their way to press it and don't misclick the button. When the photo is taken, we then set the image to the screen where it displays option save or discard, where save saves it to the user's photo gallery, where the user then can import the image into a block through the gallery or do an image to text conversion on it. If the user selects discard, it clears the photos by setting it to null.
The backend REST API for NeoNote is implemented using the Java Spring Boot framework. Spring Boot offers a well-rounded, efficient, and productive framework for building Java-based applications. Additionally, the integration with Spring Security allows for thorough authentication processes to ensure that NeoNote's users' data is kept secure. Spring Boot's extensive features, strong community support, and ability to streamline the development process made it best choice for developing the backend services of NeoNote. The database architecture follows an MVC structure with additional layers for data access and logic. The system is structured into entities, controllers, services, and repositories. The entities represent our database models, including attributes and get-set functions. Repositories handle data access, allowing for CRUD operations to be executed without the need for SQL queries. Controllers manage HTTP requests and responses, defining the endpoints for our API. And lastly, our services contain any associated logic and allow for communication between our controllers and repositories.
How did we decide to store the data created by NeoNote? Due to the nature of our project requirements, our team established that cloud storage would be best suited to our mobile application. Like all other aspects of NeoNote, we wanted it to be easily accessible for anyone, anywhere who wanted to download our application. With this in mind, we selected Google Cloud SQL to host a Postgres instance as our main database, as well as a Firebase Cloud Storage to host a bucket. We selected two different cloud storage options, as Postgres would offer us the benefits of speed for relational data queries, whilst Firebase Cloud Storage offered a simple solution to store our unstructured data, such as images and audio files. To store our data, we have three tables in our Postgres instance, namely collections, notes, and blocks. We've kept our data structures very simple, where each user has a collection to store their notes, and each note stores their corresponding blocks. Within the blocks, we've kept our data fields as simple as possible, with unique identifiers for all object IDs, as well as a collection storing only an array of its child notes and their corresponding unique identifiers. Each note storing the title is a Boolean is favorited value, and an array of its child blocks with their unique identifiers. Each block stores its content type, namely text, image, or audio, as well as the relevant link to any multimedia data that is stored in the Firebase bucket. We can have a quick look at our Google Cloud SQL instance, and we can see that we have our ID is favorited, the title, and its collection ID, as well as it last updated. So if we have a look here, this would be the ID for a note, and to access our block stored in our Firebase bucket, we can just request to use this note ID and get the corresponding blocks for that note. And so here we have our unique identifier as seen over here, and then we can see that this is just an audio file we have stored in our bucket. This is how we decided to store the data for our NeoNote application.
To provide security for our application, we've used Spring Security along with Firebase authentication. With Spring Security, we've defined a custom filter to authenticate any incoming HTTP requests. This filter extracts the bearer token from the request headers and verifies it using the Firebase SDK. Any invalid requests will be rejected and returned a 401 error. As a result, they will not be allowed to access any resources. Here's a quick demonstration of this process in action. Here I have two tokens, the first one being a valid token and the second being invalid. Both of these were provided by our system. However, Firebase requires tokens to be refreshed every hour. So therefore, even though this token was valid, it no longer is, meaning that if someone does get access to these tokens, they have only a very small window to where they can access resources. So using this token here, we're going to attempt to access a collection for a user, and we get a 200 OK and have access to the resources. If we use our invalid token, we get a 401 unauthorized error, meaning that whoever sent this request does not have access to any resources. To deploy our backend services, including the Fast API and Spring Boot applications, we're using Docker for easy deployment. By Dockerizing both of our services, it means we can install them and all their dependencies with one command. As we can see here, both services are up and running. To deploy our application, we use 2 Docker files, all brought together by one Docker Compose file. These files tell the server to install all needed dependencies and run the applications using a given command. For our fast API, we create a Python image, we copy all the files across, download the Tesseract dependencies, create a virtual environment, install all of our requirements, and then finally run the server. For Spring Boot, we do a similar thing where we download an Ubuntu image, install JDK 17, and then run our pre-built application jar file.